Thank you very much. I'm going to talk about my research and things I came up with that are part of my habilitation thesis. Is work that has been done in collaboration with these people at various points in space and time, and I gratefully acknowledge their contribution to what I'm going to talk about. So this is the thesis to be defended. When I posted this image on Facebook, one of my friends said that she misread this as funny field. I'm going to let you be judges on how much fun this is going to be. And if you scan this QR code, you will find my thesis, the papers that are mentioned there, and some other stuff. So if you get bored, you can flip through or yeah. So you can scroll through the thesis on your own. And so again, what I would like you to remember is that if we quantize gravity, we end up with quantum space-time. Fuzzy spaces are examples of such spaces. Those are the bubble spaces that I mentioned in my previous presentation. And there are interesting things happening there. We can study the consequences of this quantum structure. And fuzzy spaces have the advantage of the physics being described by matrix models, where we can actually calculate things and come up with results that can be underlined and published. Basically, my previous lecture was quick motivation to why to study these things. We need to quantize gravity, but when we use the standard procedure on general relativity, we run into trouble. And no matter which way you try to solve these problems, one way or another, you obtain notion of a space-time with some characteristical length scale and some minimal length scale. And there are some ways how to see this beyond that. And fuzzy spaces are examples of such spaces where you can do some physics. So let's do some physics. And fuzzy spaces on their own have appeared in various places in mathematical and theoretical physics, starting 100-ish years ago in the dawn of quantum field theory, and then at plenty other places elsewhere. But for what I'm interested in and the way I'm presenting these results, the last point is important. That is a model, well-defined model of a space with quantum structure where we can actually calculate things rigorously, and therefore we can hope to learn some lessons that we will later take when we construct more realistic theories. But with asterisk related to this, where fuzzy spaces actually do appear as solutions of some models that are more than toy models, that are matrix models motivated by string theory, where you end up with fuzzy spaces as solutions for your space-time degrees of freedom. So I'm going to talk about fuzzy sphere most of the time, which was constructed by people that we know and love. And the point is that on a regular round sphere, the information and everything you need to know about that sphere is encoded in the algebra of functions, where YLM are the spherical harmonics, which are eigen functions of the spherical Laplacian. So if you know the Laplacian on the sphere, you can construct this algebra, and then this algebra includes all the information about things happening on the fuzzy sphere. And what you find out when you play with spherical harmonics is that if you want to describe features at shorter and shorter length scales, you need to take more and more L's in this expansion. Yeah, you see here spherical harmonics for greater and greater L, and you can see that the patches where the spherical harmonic changes get smaller and smaller, and therefore, for example, with this function, you can describe features on the sphere roughly of these sizes. And then to construct space with finite resolution, the idea is obvious. You take and you cut off your spherical harmonics at some cutoff angular momentum, and bam, there goes your spatial separation under these length scales. So for example, points do not exist anymore because points before were encoded as delta functions in that algebra or as a limit of sequence of some narrower and narrower Gaussians. And here, since you do not allow Gaussians under certain length scale, you cannot construct these delta functions anymore. But these objects do not form an algebra. They're not closed under pointwise multiplication, because if you multiply these two things pointwise, then you obtain something with greater L. So you created an object that's not really an algebra, and you cannot view this as an algebra of functions, but there's a way to save this, and using some group theory or some just counting on your fingers, you can construct a mapping from those spherical harmonics up to angular momentum L onto n times n Hermitian matrices. And what you now do is you map your spherical harmonic onto a matrix. You multiply these two as matrices, and then you use the inverse map to see what this corresponds to as a function. This star product is by construction, or under this star product, the algebra is by construction closed. So you have a nice algebra, but the price you had to pay is the non-commutative product in between the elements of the algebra. And you kind of see that in the large L limit or N limit, you recover the round sphere. There's more to this that people in math building are interested in, but those people have rigorously shown that this thing happened. On a more technical level, I just want to flash this slide here, is that you can work with the commutation relation, and with the same algebra can be equivalently constructed like this. Here is your theta, the non-commutativity parameter, and when you realize these as spin S n-dimensional representations of SU2, you can find out that your theta goes as 1 over n, so you see that n goes to infinity is the commutative limit of this. And thanks to non-zero commutators, you obtain some kind of uncertainty relations. And I show this because this is a tip of an iceberg of quantization of Poisson manifolds, where you can quantize also the plane using either the commutation relations or a different star product. Either way, one way or another, we have turned a round continuous sphere into something with discrete structure, but not structure like this, but structure where the Planck cells are, the boundaries between the Planck cells are not sharp, but are blurred or fuzzy. So let's do some physics on this space. And I'm a theoretical physicist, so for me, physics is scalar field theory. So you take your classical, this is action for classical Euclidean field theory, and the questions that you ask are answered in terms of functional correlation values, correlation functions, and everything is hidden in objects like this. And now you turn this into non-commutative theory by taking your commutative to non-commutative dictionary, and your field becomes a matrix, your integral becomes a trace of this matrix, and most importantly, your path integral, your functional integral, becomes a well-defined matrix integral. This is the upshot of the whole process. That now these things are made finite dimensional matrix integrals, which can be either analyzed by some Monte Carlo methods, or things can be calculated precisely using the matrix model techniques. And there has been a lot about this written quite some time ago. I still have a copy of this book that I printed out when I was doing my master's thesis. And I have Peter Preschneider's notes written in there somewhere in my office. So this has been around for quite some time. And you start asking questions, and you obtain frightening answers. For example, you find out that the spontaneous symmetry breaking of the non-commutative theories is different from commutative case. What does this mean? This is a phase diagram of two-dimensional classical, and when I say classical, I mean quantum, obviously, but I mean commutative field theory. And this is not dissimilar from Higgs mechanism, that in certain parameter space of this theory, the quantum fluctuations are large enough and the field doesn't oscillate in the true minimum, but oscillates around the false vacuum phi equals, or the expected value of phi equals to 0. But here, the wells of the potential are so deep that the quantum fluctuations cannot take the field outside from that well. And in this parameter region, you obtain a broken phase where the field oscillates around some non-zero value. Now, when you do this on fuzzy space, you find out that there's a third phase, a striped phase, where the field doesn't oscillate around one single value in the whole plane. And a lot of works have found this out, and there's a nice review by Marco Panero here. And this is an image from one of those papers where you can see that here the field oscillates around one value, here oscillates around another value. So this phase breaks the translational symmetry, or in the case of fuzzy sphere, that is the rotational symmetry, in a spontaneous way. That the action is symmetric, but the vacuum, the solution of the field equations is not translationally symmetric. And the phase diagram looks like this, where here you obtain a third region where the field oscillates in different places around different vacua of the theory. So keep this in mind, this is going to be important later. But the first point is that non-commutative field theories have different spontaneous symmetry breaking patterns, different phase structures, and especially there is this strange phase appearing here. Now, when you compute the correlation functions, you use the standard Feynman diagrams, and you find out that strange things happen when you pair legs that are not next to each other. When you create non-planar diagrams, you obtain divergences that are unexpected, and they're related to the connection of the short distance and large distance physics. I like to think about this in this way, that when here you have a quantum fluctuation that is very short in this direction, then it not necessarily spreads out in the other direction because of the mechanism that I mentioned before. So UV physics here, very short fluctuations here, can transfer to place that's far away here. So the long distance, the IR physics at this point is related to things that are happening here because of the non-commutativity and non-locality of the problem. So technically, it's because of the non-planar diagram, and you can show that when you do all the things, when you calculate all the things in your theory and you come up with one loop effective action of the theory, it has a term that doesn't vanish in commutative limit. So when you compute your one loop effective action in non-commutative theory, you get some expression. And when you do large N commutative limit of this one loop effective action, you obtain something different that was effective action of a commutative theory. So the space forgets that it was fuzzy in the non-commutative limit, but the physics that lives on this space remembers its fuzzy origin. And we will see some explanation of this later. And how do random matrices enter the picture? Well, I have already shown that. The correlation functions are matrix integrals. So what you're doing here is essentially computing expectation values in a random matrix model with some very specific probability distribution. Now, without this kinetic term, answers for this matrix model are well known and have been known for quite some time. Basically, the fact that this term is complicated and requires some special treatment is the reason I have a job and the reason you are here today. And so if F doesn't depend on the angular degrees of freedom of the matrix, then what we need to do is we need to somehow compute this angular integral. This is function of the eigenvalues of the matrices only, and this can be done, and it has been for the first time done quite some time ago by Denjo and Christian. And then later, this is currently the best result we have for the perturbative calculation of this integral. You expand this exponent in powers of epsilon, you do the group integrals, and then you re-exponentiate. And so this is a matrix model that we now are going to try to calculate something in. And perturbatively, it's problematic. Perturbatively, it doesn't give the results we would like to see from non-commutative field theory. So this is where my thesis comes, and this is where I'm going to give you the first set of results that's mentioned in my thesis. And the idea is goes back to Alexios Polychronakos in the department where I did my PhD. So there's some relation there. You can do a different approximation, that you don't go to arbitrarily large moments. Here, these are the moments of your random matrix, and you can see here you have fourth moment, third moment, etc. And what you do is you just take the second moment, and the part that depends only on the second moment can be treated in a consistent way, and you obtain something that's still an approximation, but it's not a perturbative approximation. And then you introduce the asymmetry in the model by taking a shifted second moment, and you're going to analyze random matrix model like this. Now, this has been a lot of work, as you can see. But eventually, we have been able to, after a lot of technical work, see some things in this matrix model. And in this paper from 2015, I have been able to also show that under no circumstances this perturbative model is going to explain the properties of the non-commutative field theory that you're looking for. That this is necessarily not going to do the job, and you need something non-perturbative, and this is a non-perturbative approximation that we're going to use. And this is a very strange moment in my life, because basically 10 years of work are condensed into 3 lines in one image. That's life, I guess. So this is a phase diagram of this matrix model. That here in this region, the matrix has 2-cut phase, where the eigenvalue distribution is supported on 2 regions. Here in this region, it has symmetric 1-cut phase, where the eigenvalue distribution is supported on 1 symmetric interval, and here there's asymmetric 1-cut case, and I guess you can extrapolate what that means. Now, when you compare this image to this image, this is basically one of the results of my thesis, that matrix model that I have shown you reproduces a lot of features of this phase diagram that has been observed numerically. People, some of them in this room, have found out that this is the phase diagram of the theory on a computer, and some other people, some of them in this room, have found out that this is the phase diagram of that multitrace, of this multitrace matrix model that I have shown you. You can see that they're quite similar, but not completely. So this is what I called a qualitative, not quantitative agreement, that what's the important feature is the triple point of the theory, that these 3 transition lines intersect at some finite point at finite values, non-zero values of the parameters. And there are actually the 3 regions of the 3 phases here. There's this asymptote, that this red line doesn't go all the way to infinity, but it asymptotes to this. And the location of the triple point is at the correct place in the coupling direction, but it's roughly by a factor of 7 greater than the numerical value in the mass parameter direction. So this is not great, not terrible. That I have been able, and with Maria, we have been able to show that as as first people analytically that there is a nice multi-trace matrix model that reproduces this phase diagram, most importantly the asymmetric one-cut phase, and that it does have a triple point. We have been able to pinpoint the triple point and show that the location of the triple point is in the region where we would expect it to be. So, and then the natural step is to somehow try to incorporate the information that we have thrown away before. We know something about what the effective action does for higher moment terms. So we just heuristically tried any reasonable non-perturbative continuation of those perturbative results that doesn't spoil the rest of the nice features of the diagram. And we have been able to show that this doesn't help. That no matter what you do here, no matter what kind of parameters you take here, always the phase diagram that you end up with is worse than the phase diagram that I have shown you. You can flatten this line, but then strange things happen around the origin and with the triple point, and you cannot bring the location of the triple point closer to the numerical value. So nothing like this is going to help you, and the conclusion is that you simply need to go non-perturbative. That non-perturbative results, even for higher moments, are not necessary, are not sufficient, and you necessarily need to consider some non-perturbative approach to the effective kinetic term effective action. So this was the first set of results. The second set of results is related to the UV-R mixing that I mentioned. Yeah, the UV-R mixing breaks the theory. It makes it different from the commutative theory, and in the non-compact, in the plane case, it spoils the renormalizability, and it means the theory is not well behaved. There are, however, modifications of the naive formulation of the field theory that fix this problem. And for the fuzzy sphere, essentially what happens is that you take and you by force, you can see that this is a similar expression that you have seen before. You by force take away the problematic contributions, and you obtain a theory that in the commutative limit is well behaved and is the expected commutative theory that we wanted. And the striped phase, the two-cut phase, the problematic phase in the phase diagram is conjectured to be result of this UV-R mixing. So if you analyze this matrix model, you expect that problematic phase to disappear from the diagram. And we have been able to do this when we considered the expansion of that operator in powers of the second Casimir in the powers of Laplace operator, and we considered two different versions up to the first order and up to the second order, and we have been able to show that for the first case, this is the phase diagram. The gray line is the diagram that I have shown you before, and this line is the line in the new diagram, in the new matrix model. And you can see that this region where the problematic phase lived got shrunk. It got shifted away. So it actually, we have been able to show that it is true that the modified model seems to be a model towards removal of the problematic phase and does its job of removing the UV-R mixing. And then further, if you include the second order term, you can see that for positive B, this is shifted even further away. So for fuzzy sphere, the model where you don't have UV-R mixing, its phase diagram is doing what we would expect it to do, to have smaller region where the problematic phase lives. Now, with our collaborators in Belgrade, we have been able to show that the same thing happens in a model that removes UV-R mixing on a non-commutative plane. This is Grosse-Vulkanar model, which can be phrased also as a matrix model. And we have analyzed a model without the kinetic term. We already know what the kinetic term does. And with Benedict, we have been able to show that truly for the Grossen-Vulkenar model, the contribution of the kinetic term is of the same form as for the fuzzy sphere. So it does have the same effect on the phase diagram, and we want to see what the other term, the extra term in the Grosse-Vulkenar model does. Now you can do this integral, you obtain some kind of crazy matrix model, multi-trace matrix model, which however by now we're quite used to analyzing, so there's not matrix model too hard enough for us, and we just go into it and we obtain a phase diagram. And this is from the paper. So the mass parameter goes the other way. So this should have been flipped upside down, but then the letters would make no sense. So, but you can see that the original phase transition was somewhere here, and the problematic striped phase lived in this region. And you can see that the transition lines got shifted upwards. So the problematic region of the parameter space also starts to disappear. It recedes, but it recedes in a little different way. Let me show it in that original one. That here on the fuzzy sphere, it recedes in this direction. It moves to the right. In the Grosse-Vulkenar model, it moves downwards due to the curvature term in the action. And we have been able to also analyze the model by Monte Carlo methods, and we can see that that up to a certain point the model does well, and then the phase transition line does strange things, which is the same thing that happened on the fuzzy sphere that I mentioned a few minutes ago. Okay, and the third set of results is it's just one paper, so it's a result work with Harald Steinacker, which goes in a little different way. It doesn't analyze the first two sets of results. Were analyzing the phase diagram of a matrix model that has ambition to describe features of fuzzy field theory, and we have been able to show that those matrix models do reasonably good job. Now this is different, and this rephrases the matrix model in a different way. We introduce a different basis in the matrix model based on coherent states, and we parameterize the matrix by not by the entries in the usual basis, but by function of two variables. And these states are then form the basis in the space of matrices, and these are called string states. And the important thing is that string states for points close to each other that we call short states are essentially your classical modes, are the modes that become the standard modes of standard field theory in the commutative limit. Now, long modes where the points are far away from each other, they don't have any reasonable commutative analog, and they constitute a truly non-commutative part of the theory. And in the large n limit, these are scaled away. In the large n limit, these seem to disappear, and all you're left with are the short modes. Or are you? Because now there's some technical stuff that maybe, if there are questions, we can talk about later. But the point is now, in terms of these string states, you can formulate your field theory, propagators, vertices, and everything. What I want to emphasize is that this string modes formalism brings the best of the two worlds. The standard field theory world has problems with the interaction term, but it's well capable of describing the free theory. The matrix model has no problem with the interaction. It just has a hard time describing the kinetic part of the problem. And now the string modes are able to somehow capture both these things together. The price we have to pay is the bilocal function that describes your matrix. That your matrix is now described by a function of 2 points on the sphere and not only one. Okay, so this is the interaction vertex. You can do all Feynman diagrams, shenanigans, and you find out that these two diagrams at one loop are very different. You can compute their contribution, and you can show that there is this strange non-local contribution to the effective action. That's exactly the UVR mixing correction that I was talking about before. But here we can clearly see the physical effect. That here, if you have a classical theory, the standard commutative theory, and you have a state of commutative theory coming in, you will end up with a state of commutative theory going out. But in your loops, even if you're in the large n limit, at finite n, there are always those long states running around these loops, and those long states are the reason for the UVR mixing. That's effectively captured by this contribution. And then you can do field theory beyond one loop, which is the proper new results that we had. That we have been able to say a lot of things about that field theory beyond one loop, which was very complicated at the group theory level in the original language. For example, we have been able to show that the contribution of these two diagrams is what you would expect. And most importantly, we have been able to show that this diagram is even more non-local than the contribution of this diagram. That when you insert these non-planar loops, you get contributions to effective action that's more and more non-local, and we have been able to show that contribution of this diagram is even more non-local than contribution of this diagram, and we have been able to confirm the idea that the non-locality comes from long strings running around non-planar loops. And the more non-planar loops you have, the more non-local contribution you obtain. So I'm going to repeat the take-home message again. I'm going to just flash it there for you. And just to show that this is not the end of the story, this is merely the beginning. There are plenty of things that we can work on. Some of them we are already working on, and some of that stuff will be mentioned by Samuel again later in this afternoon. So normally this would be a place where I would thank you for your attention, but this is not a normal setting, so let's go with the attack, since this is a defense.